So ladies and gentlemen, dear colleagues, welcome. My name is Deněk Hanzálek and you are watching the 54th talk of the scheduling seminar. Today I'm happy to introduce Laurent Perron from Google France. So we have, let's say, industrial talk. Laurent got his education at École Normale Supérieure in 1995 and PhD at Paris Sud University in 1997. So le vieux combattant, let's say. So he was with iLog for 11 years and he finished in 2008 as a chief architect of CP Optimizer in iLog. And then he moved to Google, where he is for 16 years already. And today he is on a position of tech leads of the operations research team in Google. So he is interested, obviously, in CP. He wrote CP Solver in iLog, CP Solver in Google, which is, let's say, general purpose tool for optimization problems or operational research problems. And by the way, he's enthusiastic FIFA player, so he can tell you more about that. And Laurent, it's great to have you here, and please go ahead.
Hello, thank you for having me here. So happy. I mean, I wanted to be there for a long time, and I'm very happy you invited me. So I will present something we started a few years ago, much after I joined and actually created the OR team in Paris. So this is the full outline. I will not go through all the section in details, but for the record, some of them are interesting. So I briefly present our tools, which is the suite, open source suite, where you can find all of these. Then I will explain the design of CPSAT. And one of the important features of CPSAT is actually it's also a MIP solver, and I will explain how this is done. And because this is a scheduling seminar, I will explore some of the aspects of scheduling on CPSAT, both on top of SAT and on top of MIP, and how it interacts, and then I will give my conclusions. So OR tools, I started that, asked for the authorization in 2012, I believe, 2011, something like that, a long time ago. Vincent and I did that. Then Corentin, some of them know him as Mizux, is very active on the mailing list of people who are using that. So the OR team at Google, we're a team of 40, started a bit more than 15 years ago with one mission, which is optimize Google. And we do it in two ways. We do tools and we do consulting. And let's say we are busy. Otherwise, we'll not be 40. And there are some other teams doing OR, a bit more applied. There's one in platforms and one in networking. There's a sister team in New York. People know some of the other people there. And we're working. And if you look at there's a big book, OR, ORMS, I think, something like that, OR. And combinatorial optimization is one or two chapters of that big book. And it's already a lot. So plenty of technology, LP, MIP, SAT, CP, routing, graph. And these are just a panel of the tools that you can use. And all of the one I cited, they are part of our tools. So we have the LP solver, we have the MIP solvers, we have SAT, we have CP, we have a routing library, and we have some graph algorithms. And everything in C++. We have wrapping in .NET, Python, Java, WASM. We have some dependencies. We mostly depend on external third-party solver because some of them are really, really worth it. So Ruby, Skip, Coin, simplex, Express. It's, as I said, available in C#, Java, and Python. That's nice. One word about the ecosystem. I actually seeing the two sides of a coin, the academia part and the industry part, and I see what they ask for. So C++ has some users, some of them, mostly I would say software integrators. where we want to integrate our tools or one of the libraries inside their software. Academia, it's nearly always Python. There's some Julia, it's a niche, but they're very enthusiastic. So we see that. We don't have yet a Julia wrapper. The industry has changed a lot in the past years. .NET is still there. I don't think it's decreasing a lot, so it's still holding. Everything else is Python. And I was never, I thought about that, let's say 4 years ago, but now even big projects are all in Python. So that's it. Some startups, some smaller teams, they use Go, they use Node.js, some Wasm because it's easy to use. I don't see Java anymore. I think there's still huge projects in Java, but they are just in maintenance mode. I've very, very, very rarely request on Java, unless it's one of every 5 years we do a bump cycle and then there's questions. And C++, as I said, I think it's there. I nearly got no question except for integration. One of the tools inside our tools is CPSAT. So why CPSAT? This is 5-6 years ago, 5 years, no, a bit less. 5 years ago. And when I joined Google, we were hired to do the routing of street view cars. And to do that, we built a CP solver and a routing library using local search on top of the CP solver. So I built the CP solver, and Vincent, who came with me, built the routing library. And this is the yellow curve on that graph. So graph is inverted towards the usual. It's number of problems solved by time. So the perfect solver is a flat line on the bottom. And then we started rewriting. I realized, so 2012, I applied to the Minizing competition, which is a yearly competition in the Constraint Programming community. It contains very diverse problems: linear, Boolean, scheduling, integral. It's only integral. There's no continuous variables, set variables, anything. So it's quite interesting to write a solver on top because it helps a lot. And when I started participating, I look at the result, and there are actually two sides to the results. One is the visible part, where at that time G-code was the best solver. Then Opturion came in and things like that. And the other part is that because it's a voting system, and there are some solvers that can vote but cannot win because they are owned by the organizers of the team, of the challenge, which was NICTA at that time, and now it's University of Melbourne. And chuffed was this solver, and there's a reference in the slides where you can find actually the source of all my work. And this solver was crushing everybody else. G-code was getting, in the voting part, was getting 800 points. I was 700 points, and chuffed was 1200. So chuffed was beating everybody consistently. And so I came back from that conference and I said, okay, we have to do something, because I'm at the best I can do on the CP solver. I've optimized all the constraints. I've optimized everything. It was a pure tree search implementation, no local search, no generic local search, but this is the best I can do. I cannot do more. And I'm being crushed. And so I said, we need to invest in that technology. And that was the start of CPSAT. So I wrote a SAT solver just to understand. And then Fred came in, rewrote everything. And this was the birth of CPSAT. And so what we see is that the red line, which is single-threaded CPSAT, in 15 minutes, the CP solver solved 230 problems. The CPSAT solved 230 problems in 0 seconds, and then solved around 440 problems. So nearly twice as much. And the parallel version, which was a portfolio-based, not as advanced as now, was still winning something like 50, 60 problems more. So there's a big gap just switching the backend, because it's still CP. You still have your old diff, your scheduling constraints, everything on the top is the same. It's just the search is different. And actually writing a constraint is a bit more complicated, but that's part of the game. So what was the influence of CPSAT? The biggest one is actually closed learning. It's SAT. So the revolution introduced by Marcus Silva in 1999-2000, working on GRASP and trying to refine how GRASP worked. And he discovered the idea of conflict-directed closed learning, where actually you explain everything, you trace everything, and so when you have a failure, you create an exact proof or explanation of why of this failure, and from that you can derive a no good that will kill an exponential subtree of your search tree. And that's a real revolution. And the best way to realize that is that before 99, the best SAT solver were random solvers, local based, random walk, and you could not beat that. And after closed learning solver, except on random instances, because they have no structure, no specific structure, closed learning wins everything. So you never see random solvers winning against a closed learning solver on an industrial benchmark. Of course, since then, time has passed and all the solvers have become much more complex. All of them have the portfolio of workers. Some of them have some local search. It's a bit different, but at that time, this was a complete breakthrough. And this breakthrough can be transposed to the rest of the discrete optimization community. So CPSAT is the re-implementation of a CP solver on top of a SAT solver. And along the path, when we were writing CPSAT, we actually added a simplex and started to make CPSAT not a MIP because there are no continuous variable, but an integral linear solver. And it's also max SAT solver because we take that. Now, if you look at the literature, and actually some of it was done in iLog, there's a big research end of the 90s around hybrid solver. And hybrid solver were actually a mix of MIP and CP. And it never worked. It never worked because simplex is too expensive. And in a MIP setting with purely linear constraint, because you can create cuts, you can gain some of the same benefit as CPSAT, where you don't replay the search mistakes all the time. But on the CP, if you are on the CP part where you cannot have this geometric interpretation that will help you a lot, then having a simplex just slows you down and never bring enough value. But because this is now closed learning, when you learn something, it has a profound impact on the search. And this impact is multiplicative. If you learn different things, they reinforce them, and they kill more and more exponential subtree of the search tree. So the effect of closed learning reinforces strong propagation algorithms. And this way, even if the simplex only rarely finds things, the things it finds are so impactful that it's worth having the simplex on by default. And everything I talk, except for the simplex part, has been inspired by chuffed. And there's a very good CP 2013 presentation by Peter Stuckey that explained the genesis of all this project. And we did a masterclass in 2020 at CPIOR. It's on YouTube, and you can see the origin of that. So how is it architectured? There's a SAT layer, purely Boolean variables, clauses, and that's all. And of course, the search part. On top of that, you want to do integer variable. So integer variable, I will explain that in the next slide, but basically you have one Boolean variable per x greater than constant and one Boolean variable if needed for x equal value. And on top of this layer, you have two objects. One is a constraint programming that talks about propagators and Q and all these constraints. And the other one is a simplex, so that talks about linear relaxation, cuts, branching strategy based on a floating point. And these two are actually side by side. And on top of that, and that's actually one of the biggest strengths of CPSAT, is actually the portfolio. So there's a portfolio of very diverse search workers. One will have 0 LP, so it can be fast. One worker will have full LP, so it will be slow, but at least he will discover much more facts. And because there's communication between all the workers, when he discovers some fact, he will give that to the other workers. None of the workers shared the same tree. They all start from scratch. And some of these workers are different. There are some pure primal workers, so dedicated to first solution, large neighborhood search, local search. We have implemented something on top of something called feasibility jump, which is a violation-based local search, which is very, very good. So some of our workers are full solvers. Some of our workers are primal solution. Some of our workers are first solution only. They could be highly randomized restart type of workers. Some of our workers don't actually search. They just do probing, or they try to prove that they try to solve a problem where the objective is fixed with mean value. So either you find a solution, lucky you find the optimal solution, or you don't find the solution, and then you can bump the value of the objective. So all of these, they all collaborate, they all have their strengths, they all have their areas of type of problem they're good at. We have workers dedicating to scheduling with very strong propagation. We have workers dedicating to MIP. We are working dedicated to pure Boolean problems without any slowdown because of expensive algorithm like the simplex. And all in all, some of them will find something good and it works. Note, CPSAT is not very good if you just use 1 or 2 workers. The minimum to be usable is 8, I would say, except if the problem is simple enough, but that's what you want. So as I said, you need the second layer, integer variable on top. You have one which is dynamic, so you don't create a Boolean variable per se, only when you need that. So it's variable less or equal than a constant. The negation of that is variable greater or equal than a constant, and this is used to encode the bounds of an integer variables. And you only attach this, we call that integer literal. We only attach this integer literal to a Boolean variable when it's using a conflict. The value encoding, which is variable equal value, and is negation variable different than value. This one is statically decided. During presolve, we expand the domains if the constraint use that. For instance, an element constraint, the index will be expanded into a set of Booleans, and each Boolean will imply that the target is equal to the element in the array. And so the value encoding is static and decided at presolve, and the order encoding is dynamic. There are other encoding possible, log1, different versions. It's very influential. There's something called pcat-sat, which is a static encoding of CPU problems on top of SAT using the pcat language. And they are actually quite good. And because they are much less advanced in terms of techniques implemented, the fact that they are this good means that they're doing something good and the encoding matters. So when I present that to the CP community, the bad news is that actually I really do not use a lot of CP constraints. So CP constraints, the most well-known are element and tables. None of them are passes through the presolve. They are all expanded into inequalities and table and clauses. Automaton or regular, this one is expanded. The inverse is trivially expanded. The old if is nearly always expanded unless you have few variables and lot of values where you don't want to create just the matrix with exactly one or at least one on the column or rows. Reservoir is expanded. So when we pass this phase, we are in the kernel of the solver, which is Boolean constraint and or an XOR. Linear constraints, and these are indicator constraints or half verified constraints. You can have Boolean or negation of a Boolean imply linear constraints. Arithmetic, product, division, and modulo are there. Modulo with a fixed argument is still there. The rest is expanded into the residual of a division. All diff in the case where not expanded. And now what actually really stays are the scheduling constraints, overlap, the accumulative, and overlap 2D, and the routing constraints, Hamiltonian path called circuit, and VRP constraints, so multiple Hamiltonian path and a depot called multiple circuit. And the last two, min and max, they were there. We think we will remove them and just use the MIP encoding where you have one Boolean variable per options, and it implies that this is the one that is supporting the value of the target. So not much left in the CP world. Pure CP, really not much. CP plus scheduling plus routing, yes, so some of it is still there. And the result is, I would say, the best of everything. So from the MaxSat, SAT and MaxSat community, we benefit from closed learning, of course. There are some specific presolve technique called model reduction in the SAT community that are really useful. And the thing that is really orthogonal is core-based search. So it's a bottom-up approach using logic and not just searching for the mean of the objective one by one. It's a bottom-up approach. Is very good, and it's completely orthogonal of what other solvers are doing. So sometimes it's the one that kills your problem, and we're really happy to have it. From CP, we use the modeling language, which is really interesting. One, because it's a bit closer to the application, but two, because sometimes we don't need to play the game of rebuilding the structure of a problem. I mean, if you have a RCP-SP problem and you tell the solver that this is a cumulative, this is a resource, this is a recipe, and it's much easier to have the right algorithm in place to solve that. If it's a pure MIPS formulation, then it's much harder. So it's worth it. And all of this, especially in scheduling, we have some very, very strong algorithms to do some propagation, and we use that. From the linear integer programming community, and this is the most mature community of all we're talking here, huge endeavor to implement that. Linear relaxation, cuts, presolve, so many techniques, branching, so many things to implement, so many things that matters. I had implemented presolve for the flat zinc mini zinc challenge in the original CP solver and before for that solver. Now everything is in the SAT solver, but I had implementing presolve, but none of that technicality of me presolve. There's no dual reduction where you realize that a variable can take any value, so why not fix it? Because you can always rebuild a solution from there and it will not change the objective. So there's so many things that simplify the problems, remove solution, but not the optimal one. And these are very, very powerful. And finally, we benefit from the meta-heuristic community. Some of the workers, when you launch in parallel, will do local search or will do line-level search. And this is useful. It's actually, I think, why we are somehow competitive with simplex. If a problem is a bit hard, a bit large, not too much, but a bit large, and feasibility is an issue, then actually we are much better at finding solution because large table search kicks in and finding solution fast, much faster than simplex, than Gurubi. So finding good feasible solution on semi-intermediate hard problem, usually purely linear, we are usually very good. Grain of salt, always counter examples, but that's where one of the pattern where we see CPSAT being a very good MIP solver, integral linear solver. Why this is hard? So that's a slide for my hierarchy. Why this is hard? It's still combinatorial optimization. You're all there. It's all NPR. We know that. The thing that worries me is actually the loss of knowledge, and this is especially true in the MIP community. There's nearly no research, and there's nearly no PhD, And when a PhD has proved that he can code something, he's instantly hired by Gurubi, Mosaic, Express, Cardinal Opt. And everything he does now goes into the commercial world, which is closed source. And there's nearly no publication unless it's 10 years after the fact. So the knowledge of MIP solvers and how to solve MIP problems is actually decreasing a lot, very fast. I mean, the simplex team is no more. People went mostly retirement or Gurubi or Cardinal Opt or I think Express. So they dispatched to the other three, 4 players, but nothing comes out in the open. So there's some cuts in Gurubi. There's just a name. We don't know what it does. Nobody has a clue. And so this knowledge is being lost, which is really bad. Now, when you solve a problems, you want to find good solutions. This is luck. I mean, you try to bias your luck and to mitigate, but it's luck. You're lucky or not. And you want to prove optimality. This is math. And this is aggregating all the information around the problems to do that. And all the software I cited, so Gurubi, Simplex, CP Optimizer, worked on, all of these are hundreds of work years of investment to actually get to that state. CPSAT is 10 to 12 work years of effort. And I always wonder why there's no more of that, because over the years we have proven that this is a good way to do optimization, discrete optimization. And one explanation is that it's extremely hard because debugging is a nightmare. If your explanation is too strong, then you can miss the optimal solution sometimes, and extremely hard to debug. And if your explanation is too weak, then it's too general, it's too vague, and so you have a big slowdown. And so every time you make a bug in your code, VFA may be visible delayed. So debugging is really complex. So where we are, MaxSat, so we don't participate in the challenge. We could, not that interesting, especially since now the challenge is mostly about tuning and portfolio and tweaking, and not that many big improvement in the technology. So not that interested. But what we realized recently is that with shared tree workers, there's the one that actually do a tree sharing and try to have workers specialize on some subset of the problems, meaning some variables that are active, and have these variables active being disjoint across the workers. So on this, we are extremely good at proving inside problems. So the one that come from circuit verification, incredibly good. So we're really happy about that. CP, chuffed was winning easily. We had more than chuffed. We have the simplex. We have more advanced work, more effort. So we win easily all the gold medals since the last 6 years. Integral linear programming, I would say we are best at every open source solver around there. Remember, no continuous variable. We can emulate those, but it's not great. I'd expect Gurubi to be better. I hope we are good enough. That's what I'm seeing from the users. They use it because it's free, it's good. And sometimes it's really good. So it could be the core, it could be the LNS, it could be the search is really complex, so the linear relaxation is really bad. And so this is a better approach for this kind of problems. Scheduling, that's the subject of this presentation. We are good. We are extremely good in some cases. We lag on some of us. So compared to CPO, we lag on expressivity of problems, some complex batch scheduling, energy scheduling, transition, complex transition, all of this, it's a bit hard. Most of them we can express, but it's a bit bulky, so we could do better. We are lacking a lot on very large scale, 1 million tasks, just find a feasible solution. We have no code to do that, so the SAS solver, we struggled to find a solution for that. On the rest, and mostly on academic benchmark, we are good. So interestingly enough, and I will explain why, we're extremely good on multi-mode RCPSP. So we close half of the open problems of MMLib 50 and MMLib to 100, which is fantastic. We are not that great on single mode RCPSP because that one is very, very combinatorial. It's not about the linear relaxation does not bring anything. So we don't play to our advantages. Job shop, we're good, really good on flexible. There are some recent papers that actually are better than us. We are better on lower bounds. So we are better lower bounds, proven lower bounds of open problems. And routing, last part, it's promising. We could have everything. We could have a good propagation. We could have a linear relaxation with a sub-2 elimination. This is implemented in the solver. We could have dedicated cuts for a capacitated VRPA for time windows, but we have not yet put the effort there. So briefly, MIP1SAT, linear problem. So why our implementation of a MIP solver or integral linear solver differs is that everything is integral. So inside the solver, apart from purely the simplex, inside the solver, everything is integral. We use int64. So we trade a nans and infinity versus overflow, but I think it's a good trade-off. And we don't need the simplex. So you can solve without a simplex at all. And sometimes one of the workers, the non-simplex workers, they are the one doing all the works because the rest is too slow. So the simplex is optional. Everything we do on top, linear relaxation and cut, is optional, but sometimes it helps a lot. So that's why we try to hedge our bets. And so we have some parameters that says no relaxation, only the easy things or the full ones. Full ones will include the scheduling, the routing, the relaxations, the product, McCormick, this kind of stuff. So we run the solver at each node, but only for a limited amount of iterations. If we converge and prove the optimal, then we can use it. If not, then we will branch. Because it's a dual simplex, we can restart, do some iteration. If we find an optimal solution to the simplex, then we'll use it and so on. And we are completely lazy in what we put inside the simplex. So we have all the linear equation, some for the model, some for the linear, some for the linear relaxation, some for the cuts. All of this, they coexist. Some of them are selected to be inside the LP active LP model. And something that is always true when we start removing something that is violated at a solution, then we put those into the active model. And so we have a dynamic. We try to make it not too big. And we clean that. The big drawback, but it's true for most of the solvers, is that what we do is only valid at generating cuts is only done at the root node because we don't know to explain the cuts because that would be too much. And if we use bounds inside the search to do your cut, so it will become a local cut, then when we use the result of a simplex, we need to record that we have used these bounds. And that becomes complex because we don't track actually which linear equation are used or not. So what do we use the simplex for? Infeasibility, lower bound of VLP, and reduced cost fixing, and some heuristics. As I said before, everything is exact. So we use the lambda, the solution from VLP as Lagrangian multiplier. Then we multiply all our equations, which are integral, with these scaled up integral multipliers, and it's always valid. It may not exactly be what the simplex wanted, but it's still valid. Then we get a big equations and we can use that. And we continue that way. Let's do that. We propagate infeasible, I said dual feasible, and we discuss thinking is there. The explanation of something that is exported to the simplex is actually the basis. So the variables that are inside the basis and stuck are the bounds, up or down. This one, because they cannot be pushed, are the one that make sure that explain why we get something from the ELP. So it can be large because it's still the basis, but it's still a condensed version or a focused version of what everything that is inside the simplex. So it's useful. And if you look at the chuffed and CP onset research, you can expand or relax some of these constraints if you have some slack. It's a bit complex, but it's useful. We have cuts, they are still integral, they are still exact. We have all the usual, the Fatal-Montgomery, the Mir, the zero curve, and then on top of that, lifting, cover, all of these techniques on top of that to make sure that we get the best out of it. And now CP stat and scheduling. So the CP scheduling on CP is a well-known thing. CP Optimizer has a very, very good track record on that. And so what's interesting is now we have a MIP. So in CP Optimizer, there's also a MIP, but the MIP is inside the solver. So it knows about the bounds, the propagated bounds of a variable. And so the question now becomes, what do I use the MIP for? Because if you look at the scheduling on MIP technology, mostly from the 80s, 90s, and 2000s, they re-implement edge finding. So you solve a problem as a MIP, you look at the solution, and you generate cuts manually that actually propagate the edge finder. But this is done by the CP. So there's no point in having all that layer that re-implement the propagation. So we use the LP to do something different. And the example is on a flexible job shop. So you have a set of jobs and a set of tasks for each job, and some of the jobs can be executed on one of many machines. And so you know that a job needs to be executed once. The task needs to be executed somewhere, and you minimize the make span. And the big problem with CP formulation, it has no global vision. So if you have only spaces for 2 tasks on each machine, but there's a job that has 3 tasks left, then it does not fit. But it's a pigeonhole problem, so you will struggle a lot to prove that. But if you take your LP relaxation and then you add one equation, which is for each machine, the set of the sum of the duration times the Boolean literal that tells you if that task is executed on that machine is less than the capacity of the make span. And you do that on all the machines. You have a vertical constraint that says this task needs to be done somewhere. And you have the horizontal constraint that says this energy is bounded. And then you don't have a pigeonhole problem anymore. And so just adding that equation, 8 threads, 15 minutes on 313 scheduling flexible job shop problems, we go from 205 to 246 problem proven. Huge impact, one equations. And so you can do more than that. So this was an example of energetic. You can lift that, so meaning you can look at tasks that overlaps your time window, and they say there's a minimum contribution. So I can add something from that task in my energetic equation. And this is lifting. You can do both more. This is combinatorially, the complexity is big there because energetic, so timetabling and square log n, energetic and square log n at best, and extending energetic, this is that, it's much more. Luckily, or that's the limitation, we only do have a route node, so we don't do that throughout the search. The most important cut I would say from all this is actually called Smith rule. It's a paper from '93 from Keran on scheduling, and the sum of the n time times the duration of a task that do not overlap is greater than a constant, and the visual explanation is you have a stair, and whatever the order of the three rectangles, the dark blue, the light blue, and the yellow, the area that is covered by all of this is fixed. So the lower triangle is the sum of the duration squared divided by 2, and the upper triangles sums to the sum of the duration squared divided by 2. And this area is fixed. And this cut is fantastic because everything else, and if you look at the linear relaxation of a scheduling problem, all the start time will be pushed to 0 because it's far away from the image span. And this task, this cut, spread the task apart, saying they need to be pushed, they need to make space between them to work. So this is for an overlap. You can rescale and have it for cumulative. You can project and have it for an overlap 2D. And you can lift by incorporating tasks that must overlap, but not fully with the time window. Now, why are we good on PSPlib, especially MMlib 50 and 100? It's because we introspect the model and realize that in the RCPSP model, when you look at a recipe in multi-mode, you have one duration and a set of demands per machine. And this is controlled by one Boolean. Is that recipe active or not? And so the energy of that recipe is a product of that Boolean, is it used or not, times the duration, which is fixed, times the demand that is fixed. And so if you use your energy inside the edge finder, you will have to use the mean energy, which will be the mean duration times the mean demand, because everything is variable. In the linear relaxation, you can say, okay, but now I won't use this product or its McCormick relaxation. I will use a linear formulation, which is a Boolean, a weighted Boolean sum. Is that recipe active times the fixed energy of that recipe? And we use that everywhere in all the cuts, in the explanation, in the propagation for the Smith rule, in the energy, in some other parts, we use these equations about recipe. And what is really nice is that these Booleans are actually the one that matters in the search, and they are linked, the Booleans in the LP are linked with the Boolean in the SAT. And these are the one that matters because this is the decision, the recipe, the mode in multi-mode that you're going to use. And it can be used also for 2D packing, rotating box will always have the same energy, some of the variation. And lastly, stronger scheduling propagation. This is something we've been looking at recently. So somebody sent me on the mailing list this problem, which is I have a cumulative, I have P task, I have K task of fixed duration P, and I have 2K plus 1 task. And my capacity has horizon, which is K plus 1/2 times P. And so energetically, the lower bound is 2. Physically, because you cannot split the last task, it has to be 3. It's extremely hard to find because all your reasoning will do, oh no, it fits. But actually, it does not fit. So we're back to a pigeonhole problem where you will try all of them one by one until you refuse. And so when you have this kind of mismatch or things that you cannot reach, energy that you cannot use, there are 3 techniques you can use. One, the trivial one, is to divide by the GCD of all the sizes, which is fixed. So that's a trivial one. So when it works, it's good because you can also divide the horizon, also the horizon by the GCD, and you will shave the half P. And so it works. But as soon as you have a GCD of 1, you cannot deduce anything. The very expensive method is subset sum. You will compute all the possible combinations and maximize the energy you can reach while within capacity. And so you can do subset sum on the sizes, you can do subset sum on the demands, you can do subset sum on the energy. Same thing, you can use all the energy of your cumulative divide by the GCD, or recently there was a good paper on overlap 2D for that, on the 2D packing. You use techniques from MIR, so super additive methods, basically divide by one constant and round down, but that constant is not a GCD. It's just something that will explicit a potential failure. So you have all these ideas. The best one is subset sum. It's very, very, very expensive to do. And now you have a question, do I apply that to the propagation? Which could be very good. And I think that's what you need to do to be very good at single mode RCPSP or non-flexible job shop. But it's extremely expensive. You can look at GCD, but it depends on the data, and most likely it will not be useful. Or you can use mere techniques, and that's where we are, and we don't know how to do better. I mean, we have some ideas, but it's a bit complex. But so you can do that at the propagation level. You can do that at the linear relaxation, which is what I did for the previous example. Or you can do that when you generate cuts. You have your time windows, you have all your tasks, you apply different rounding techniques, and you say, okay, I have a stronger formulation for my cut because I know that I will not use the full capacity of my resource. So, conclusion, CVStat is a fantastic CP solver. It's a good MIP solver. It's a good scheduling solver. And compared to all that came before, it's the first one where you have a simplex on by default. So you can do scheduling and have a linear relaxation, which is actually great. You can do routing and have a subtotal elimination cuts directly. This is great. And benchmark shows that it's a complete shift in what you can solve, at least in the CP community, and it's good. Everything is possible because of closed learning. Otherwise, it would be too costly. And it reused some of the 80s, 90s, so from Balash in 85, at least to Karan in 93, literature on scheduling on MIP. I know it's still active. I know Christian Artig presenting some very good papers 1 or 2 years ago. So it's still there. I think scheduling on MIP suffered from edge finding and all these very strong propagation techniques, but were better integrated in CP. Some of them will disagree. It's normal. The game changer for this implementation compared to, let's say, chuffed or possible overt solvers is the portfolio. Having that diverse set of problems make it really, really robust. And we could do more than just the simplex. We're thinking about, could we use SDP, so semi-definite programming? Yes, no. Could we use something else as a method for relaxation? Could we use MDDs? It could be used, and you would find something else that is not seen that by a simplex. But we also have strong scheduling methods. We have workers that try to simplify the models. What's next? We could use tools like Espresso. I mean, all these simplification frameworks. So for pure Booleans, for SAS solvers, this is useful. Can we compress our model somehow? Yes, no, maybe. There are some techniques in CSP solver, think toolbar, or think kind of solvers, where they do very clever stuff with cuts, where they actually push the cuts from violated constraint to variables, to pair variables, to single variables, so that you can increase the lower bounds. We could always improve MIP. It's endless, and as I said before, it's mostly undocumented. So when it is keep, when it's in eyes, then we can understand what's being done. And when it's in Gurobi or Express or something, we don't. SAT, I said before, that had moved. Actually, there's some recent, very interesting development on SAT solvers. So before, let's say around 2000, 2010, a SAT solver, you pass a problem, do a lot of pre-processing, and then search, and during search, find a lot of clauses, back jumps a lot. Now, SAT solvers, you give it a problem, don't do any pre-processing, everything is done incrementally. Every time you go back to restart, or when you pre-process a bit, you try to simplify your clause. So this is good because eventually you will process more with all you have learned that what you have done before. And you don't jump a lot. There's something called re-implication, where actually you add the constraint dynamically, but you don't back jump because you don't want to lose everything you've done. So it's a trade-off. So there are things that we should re-implement. Some of them are extremely hard in our context. We cannot re-imply easily with a simplex in between. But I have some notes on scheduling. We have violation-based local search. We could have pure local search. Could have better techniques. And we can work on routing, and I hope sometime we have time to do it, because I think it's promising, but it's way, way complex. And purely on scheduling, we have some first solution heuristics, but they could be improved. They are the state, I mean, the information they use is very weak. There's nothing cumulative there. There's nothing about a track of a job or flexible or energy. So it could be improved. We have some scheduling LNS. We have some basic time window based. We have the one from the paper from 2005 from Laborie and Godard on, I forgot, LNS for scheduling, where you will create a dependency graph and you break it. So this is, but we could do much more. We have very few things that actually look at the actual solution. And one good thing to notice is that if you have just as a job shop and you don't touch the critical path, then you will not improve the cost. You may diversify your state such that the next move will find an improving move. So it may be worth working on the plateau, but you will not decrease the cost. Plenty of stuff to do on the propagators. We have a timetabling, edge finding, and we have energetic propagators. I don't think timetabling we have, but I don't think the two have the best possible complexity. I don't think they have the best possible explanation, and they barely integrate some of the techniques I talked about, subset sum, GCD, mere techniques. We lack, especially against CPO, on modeling complex scheduling models, batch, temperature in the oven, this kind of stuff. And one particular aspect is everything about time sequence dependent transitions, cost, delay, accumulation, having one robot doing actually the transition that need to be on, or using space. There are many things that we could improve and we're not there. And that's all.
Okay, thank you very much, sir. It was really exhaustive. And now let me open discussion. I have to unmute participants. So now everyone should be able to ask question. So I see Nasser is unmuted. Nasser, do you want to ask something?
Yes, thank you very much for the presentation. I really enjoyed. So I had a question that I saw some part of the result on the last slide. So my question was, how far did you go for sequence dependent setup time problem in scheduling, like flow shop or just single machine? Because they are very complex. So did you have any experiment, on those problems? Thank you.
So I've discussed with team that used it. So the biggest issue is actually I have to create the matrix So the way you process sequence dependent, and there's an example in the doc somewhere that tells you how to do that, is I use the circuit constraints. So the circuit constraints takes a graph, takes every arc as a Boolean variable, Boolean neutral, and it forces that that graph to have a, to have a single Hamiltonian cycle. So you have a dummy node and then all the tasks, and you go back to the dummy node. And the way you make the link between the scheduling and the routing model is that if an arc is used, then it means that the tail is the next task of the head. And so you use the same Boolean to say the time at the next task is greater than the time at the end of the previous task plus the delay. It works fine. So the circuit constraint is used to do the transitive reduction from the precedences to the successor. This is great. It works. It's a bit slow. Actually, the slower part is the preprocessing of the square matrix of precedences that you attach. So if you have 1,000 tasks, you have 1 million linear inequation that says, if I'm using this arc, then I have precedences with delay. And just preprocessing that is slow. So it's good to find lower bounds. It's just slow to preprocess. So we need to do something about it. There's one question on the CPU continuous coefficient. It's already there in CPSat. You can have an objective with continuous floating point coefficients. Next question.
Okay, so may I ask you to open the chat, because there are maybe 5 questions in the chat.
So 2. So
but you have to read it, right? Because
yeah, sorry, yes. So for just a problem with decision variable, it will actually be generated. So the model is to have a start variable. So you have one integral variable per start of objects and one Boolean variable if it's a flexible job shop. Now, depending on which worker you're using, and if you're using the max LP, so the one with maximum linear relaxation, then we also, if it's not to be, create all the Boolean per disjunction in the no overlap. So we have 2 sets of variables, the starts and the precedence between tasks on the same machine. And we let the SAT solver decide which one to use when branching. But the base model is start variable is an integer variable. Documentation can access to study all the advanced concept. The code is actually documented, but it's not a very good answer. No, send us an email. I mean, there's nothing that hard. It's mostly specialization of techniques. Lazy constraint in CPSat. So on the me part is done by default. So everything that goes into the simplex is lazy by default. On the CP part, tricky. So by nature, the SAT engine, because of the 2 watchers, is lazy. So it takes memory, but it does not take time to propagate, unless, you need to check. So it's a bit better in that case. Should we mark that? Should we mark constraint to be only check? Yes, no, we have one special type of workers where we do max eating set. And we have a MIP model and a CPSat model. And when we solve a MIP, project the solution to CPSat, we give you a no good that we inject into the MIP. Barely better, so some kind of vendors. usually not competitive with everything else. So yes, possibly. There's so many things I like to do with constraints. I like to have constraints that do not appear in the local search because they're just redundant. I like constraints that do not appear in the simplex, who only appear in the simplex and not on the SAT. I would like to be able to annotate my model with lots of linear inequations, but I don't want the SAT to propagate them because one, they are redundant, and two, they are slow. But they could help a lot the linear relaxation. It's a global means what goes where. It's an open question right now, and lazy constraint is one answer to one particular kind of problems in Gurobi simplex. I'd say it's a bit less acute a problem for CPSAT, but I agree it's something that is asked for.
Okay, Laurent, let's go to live questions. May I ask Max Coulter to ask?
Can you hear me?
Yeah, we do.
Okay, perfect. So thank you first of all for the nice talk. I would have two questions. And so the first question would, could I like use OR tools to use, for example, on purpose, an expansive propagator? For example, I want to have like energy-based reasoning to propagate the time windows. So I then have tighter time windows I can feed into more expansive.
So sorry, it was a bit choppy. So you
I
want?
don't hear very well. Maybe, Max, it's better if you write the question in the chat and then we can read it properly, right?
Okay.
We can't really hear you. Okay, please try to type it in chat. And I would like to ask Milad De Hogen, who raised the hand. Milad, please go ahead. Unmute. You have to unmute. Yes.
Can you hear me?
Yes, we do. We can.
Yeah. Hello, Laurent Perron. Thank you for your great presentation. I have a question about the hint function that I'm using the CPSAT for the scheduling problem, and I used the hint several times, but it didn't work. It didn't make my model the solver faster. And I read your comment in the stack.
Yeah. I lost you.
We don't hear you anymore.
So I'll start answering what I think is the question.
Yeah.
So
speak about hint.
The hint,
Yeah.
HINT, and it didn't work. And you said that you use the fixed hint. And but if we use the fixed hint, but it is not hint, it is exactly like the fixing the variables. And my question is, what is the difference between the fixed hint and the variables, fixing the variables? Is there any difference between the fixing the hint? Because the hint, it didn't work. It didn't help me. It didn't make my solver faster. Can you please?
Yeah, I have an answer. So first, the API. The API in CPSAT for hints for everybody is you can specify, try to search this value for this variable. And you give that in order, and you try to fix variable in that order to the value in the hint. Now there are three situations. The hint is complete and valid. In that case, the solver recognizes that this is a feasible solution and will start from that. There was a bug, it should be fixed in 9.9, coming out tomorrow. There was a bug where you could lose the completeness during presolve, and normally it's fixed. Your int can be valid but incomplete. So we will use that, but if it's hard to complete that into a feasible solution, then we will still struggle. If the int is complete or incomplete but infeasible, we will try to follow it, but then we'll struggle to actually repair it into a feasible solution. So it could be easy, could be hard, but it's a real search. Now, there's a parameter of the SAT solver that says fix the int, and this is exactly equivalent, when this parameter is true, to saying adding a constraint variable equal value. It will fix the variable. It will use that in presolve to reduce the model a lot. And this is useful, for instance, if you have an incomplete hint, valid incomplete hint, you will use this parameter, you will solve, you will fix everything, propagate. Luckily, you could have a very simple problem to get a complete solution. And now you can use that complete solution as a real hint, non-fixed, and start a search. And the way the hint works is that we try to follow that for some times, and gradually, because of the stat search and the decay, we lose more and more. It loses more and more the relevance, and the activity of the variable that are in the hint start to decrease. And after sometimes where we don't find a solution, then the hint is forgotten.
Yeah.
Okay,
Thank you.
thank you. Let me go back to Sergey Polyakovsky. He also asked a question in chat, but probably now he wants to ask.
Yes, thank you very much. So my question is, you mentioned that real coefficients are possible. So I'm using .NET, and I don't see any interface to do this because all coefficients are expected to be of long type. Well, this is the first question. And the second question is about your 2D non-overlap constraint.
Yeah.
Have you compared bin packing on benchmark instances, so maybe with some MIP exact techniques? How competitive is your constraint?
So we worked a lot for this release on 2D bin packing, especially introducing some of the techniques I talked about. I use the original benchmark from Martello and Todd. So the class 0, 1 to 10 examples. When I started, the result I had, so 2 years ago, was there's 500 problems. There was 60 unsolved, and we were proving all but 30. And there's a recent paper, I think last year, where they use a two-phase decomposition model, where they solve all by 20 in 1 hour. And with CPSAT, with workers, which is not the case in the other approach, I also solve between 18 and 21. I mean, I also solve all by 18 or 21 of the same benchmark. So we use more machines, but we have state-of-the-art results on the thing. And the good news is because it's not a decomposition, it's actually a constraint of a model, you can have something else in the model, which is not possible with the approach because it uses some domination techniques. So it's good. It became much better recently. That's the point. Floating point, I forgot. There should be a double linear class. Maybe I did not implement it in C#. I'm sorry about that. You can trick it and add it manually to the proto. And if you send me an email, I will tell you how to do it if it's not there.
Thank you. Let's go back to chat. Max Coulter asked his question. Please go to the last two bullets. Can I tell your solver to use certain propagation techniques, such as can I tell the solver to do energy-based reasoning to obtain tight time windows? I would like to do so I can use the time windows in a larger MIP problem? Question mark.
So I will answer the second one. Can you use warm-stat? This is the discussion on hints. Yes, there's an API for that. Yes, no. Most of the constraints, especially the energetic time window and the edge finder timetabling edge finder, this one are protected by a parameter. But usually I don't use that manually. There's workers that will have all the expensive techniques, and there are workers that will not have them, and hopefully one of them will be the more useful one. But you can find great ways, and in the next release, so hopefully tomorrow or hopefully before the end of the week, you can very fine grain decide with this worker I will add this parameter. So not everything is covered by what you ask for in scheduling is there. You can decide yes or no if they are active or not. And you can say, please run this worker with the edge finder, timetabling edge finder on, and use that. It will be possible.
Okay, thank you. And Sergey, you still have your hand raised. Do you want to ask next question, or Sergey Polyakovsky? Probably not. Okay, guys. So thank you very much. It was very interesting discussion. Thank you, Laurent. It was. Yeah, I have to unmute Sergey. Still one question more.
Yeah,
Sergey,
thank
please.
you. Otherwise, I can't participate. Yeah, my another question is about warm start. So we tried with actually with Milad on a couple of problems, and even if we provide exact solutions as the warm start, it doesn't pick it up actually and generally reinstantiate this solution and achieve the same quality. Is it just part of heuristic search? I mean, this warm start, or this is a must for CPSAT to generally recreate the solution from the variable values?
So let's say in the context of semi-large scale scheduling, finding a feasible solution can be either trivial because you have a PERT and you know it, or it can be complex. And as I said in my talk, we have written some heuristics that are quite good. They help a lot compared to no heuristics, but they are not the most advanced one. So if you know how to build a very good solution from scratch, please give that as a hint. It helps. Is it a must? No. Is it useful? Yes, a bit too much. And I hope we do better in the future, but this is the current state.
Yes, what I mean is if I give an optimum solution, it does not recreate this. And
so it should be fixed. If you enable the log, it tells you at the start you have a complete feasible int. And now it tells you at the beginning of the search. So before presolve, it tells you that, and at the beginning of the search, it will tell you again, I'm using the int, it's complete. If it's not there, then it's a bug, and you send me the code, the model.
Okay, great. Thank you.
Okay. It's always great to talk to the programmers of some real systems.
Yeah, there's a very good feature. It's true for OMIP solver. You can always export to MPS, but it's not true for a VCP solver. So there's a model export feature, so you can send me the model from whatever language you're using, and it's fantastic for debugging. So it's part of the tool.
All right, so no more question. So if this is not the case, I would like to thank Laurent once more. It was really
Thank
great.
you very much. Thank you, Zenet.
Yeah, it was great to have you here. And now I would like to remind the folks what will be the next talk. It will be given in 2 weeks, March 20. And it will be given by Peter Smet from KU Leuven, and he will speak about robustness in personal rostering. Thank you very much for being with us, and hope to meet you in 2 weeks. Okay, thank you. Bye-bye.